All right, so what did we do in the friction lab? Good question, Don. What did we do? Well, I feel like what we did was you started pulling, and then you pulled until it started moving, and then you pulled it at a constant speed. Does that seem vaguely familiar?
Yeah.
Yes or no?
Yeah.
Yes. Okay. And one of the things that we noticed, okay, one of the things that we noticed was when you pulled it, so this is the time, this was the pulling force, but it's the force of friction. We got something that looked like this, where it went, and then you pulled it at a constant speed. Does that seem also vaguely familiar?
Maybe.
All right, what do we call the maximum amount of force that we get right before it starts moving? Good. That is the static friction. And then what about the force, or the friction when it's moving at a constant speed? Good. That's the kinetic friction. Okay. Now, one of the things, there were two sides of the room. This side over here, right? This is how we made the measurements. But what did you change to see if it would affect the amount of friction? This side over here, what did you guys change?
The normal?
That's right, you changed the normal force. Now, there are multiple ways to change the normal force. You could have pushed down on it. If you push down on it harder, the table has to push up harder. But I don't think most of you did that. What did you guys do in the lab to change the normal force?
Put more weight on it.
Yeah, you just put some more weight on it, right? So right now the normal force would be 4. If I put another block on it, the normal force would be 8, and then 16, and so on. Is that cool? All right. So this is how you took the data. Good job. Okay. But then you guys plotted your normal forces. This is, again, normal means perpendicular. This is the force by the surface that pushes perpendicular to the surface. In this case, it's up because the horizontal table is horizontal. And then you measured the frictional force here. Okay? And a very interesting thing happened. All right? When you guys plotted this, okay, you took the data, you plotted with the Desmos, you put it on a whiteboard. What kind of relationship did you end up seeing?
A scatter plot.
Well, they're all scatter plots, but was it like just randomly scattered?
Yes.
Linear. Okay, linear, absolutely. Right? Right? But something interesting happened is you got two distinct lines. Okay? You got two distinct lines, one with a steeper slope than the other. Okay? Check back at your lab real quick. Which of these is the one with the steeper slope? Why are there two, and which one has a steeper slope?
The second.
Have the equation here. Static friction is steeper.
Yeah. This is a result that every group that did this, okay? Every group that did this got this. Now, again, if this isn't the lab that you and your group did, I want to make sure that you have this in your lab notebook because it's going to be important. So, if you were on this side of the room, I would like to see you scribbling furiously into your notebook so you have this. Okay. So, we have two lines. One is for static and one is for kinetic. What do you notice about these two lines? What's different about them?
They're slopes.
Yeah, which one has a larger slope? The static. Remember, slope is actually just a measurement of the steepness of a line. So this one is steeper. Obviously, it has a larger slope value. Okay? What this means, though, is for any given normal force, the static friction value is larger than the kinetic friction value. Okay? For any given normal force, the static friction value is larger than the kinetic friction value. And that actually makes sense to us because if I come over here and I look back, what do I notice about my static and kinetic frictions? Is the static a larger value?
Yeah.
It really is. And this result is interesting to me because what it indicates is that it's harder, when you're going to pull something across the ground, it's harder to get it going than it is to keep it going. It's harder to get it going than it is to keep it going. one way that we visualize this is if we took a macroscopic view of two surfaces, let's say that that's one surface, let's say that's the tabletop, and then we're going to put a block on top of that. Okay? Okay? If we want to put the block surface on top of that, these surfaces might be able to fit together a little bit. Okay? These surfaces might kind of nest together a little bit. And it might be hard to get them to move. Once you got it moving though, it might bounce along the top of it a little bit easier. So if we take this macroscopic view or microscopic view of these surfaces, it can help us explain why it might be harder to get it going, than to keep it going. Does that sound all right? So far, so good? Okay. That is a understanding that it's important that you have that this static friction is larger than the kinetic friction. Okay? Kind of important. All right. Feeling good? This is all representative of the lab you did, yes?
Yes.
So, what is the, okay, it's linear, so what would be the equation for this bad boy then?
For which one?
The whole thing, either one.
Like kinetic or static?
Well, in general, it's y equals mx plus b,
Oh,
right?
oh, I thought you wanted to.
I know, I was looking for something more general. Y equals mx plus b. So what's on the y-axis?
The friction.
So the frictional force, I'll do F sub little f is equal to, what does the m represent? That's the slope, good. And then what's on the x-axis? The normal force. And what about the b value?
The starting friction.
So what do we want, what do we think the b value should be?
0.
Do we think it should be 0?
Well,
I don't know when the normal force is.
Why don't you check your neighbor on
I
this
was saying
one?
when normal force is 0.
Do you think that this intercept should be 0, and does that make sense? So take about 30 seconds, check with your neighbor, draw a conclusion. Do you think it should be 0 or not? I will poll you shortly.
Yeah, I think it's 0.
Yeah.
There's no
It is 0.
Normal force.
We can just count out.
Started up at 0. Oh, yeah.
Yeah, we can just count out.
No pushing. What? What is
Get in! Oh, suck it like.
I don't know that one.
All right.
I have not done that.
Here we go. What do we think? Does it make sense to you that the intercept should be 0?
Yes.
Yep.
Yes? Madeline, go ahead.
Whoa.
Or not. I mean, it doesn't matter. You seem very enthusiastic. I wanted to like jump on it. Go ahead.
I got nothing.
All right, would someone like to help her out here? Go ahead, Brendan.
So it's saying like when normal force is 0, what is friction? So if normal force is 0, that means there's no like gravitational force. So that means that, or there's okay, sorry, the object doesn't weigh anything. If there's no normal force, so it's not possible to have friction if there's no object.
Oh, okay. So that okay.
Am I crazy? Do I sound crazy? Yeah.
Every time you say something.
No, I understand what
If
you're
the
saying.
normal force is 0, then
Right.
the object's weight, or the weight of the object is also 0.
Okay. Possibly. Well, but like, let's think about it this way.
Okay.
How much does this block weigh? George is your mo, man. How much does this block weigh?
4 newtons.
That's right. Great job. Nailed that. I'm so excited. 4 Newton block, right? See, I even tried to psych him out, show him this side.
That was when I got it right.
He's like, it's going to be the one he doesn't show me. What does this block weigh?
4.
4 Newtons. So if it's just sitting here, with how much force is the table pushing out?
4 newtons.
4 Newtons. That is the normal force. It's the perpendicular force exerted by the surface.
Horizontal force is the?
Well, in this case, it would be the friction, but there's no, because nothing's pulling or pushing. Okay. If I pull this up a little bit, let's say I pull up with just 1 Newton of my own force on the string.
Yeah,
Okay? How much does the table push up with now?
3 newtons.
Just 3. Because if I'm doing 1, the table only has to do 3. If I lift this all the way up, I'm pulling with 4 with the string, how much does the table push up with?
0.
0.
So there's no friction.
There's no normal force, right? But the block still weighs 4 newtons.
Okay, but there's no friction.
That's right. What Brendan is saying, and I agree with this, is if there's no normal force, that means the block is not touching the table. Right? It's not touching the table. And if it's not touching the table, there can be no friction. So this is our framework right here. Got it? So far so good?
We got like 1.5.
Now, you guys did this and you got different slope values. Alright? Alright, so who's working at this first table here?
That was us.
Okay, what'd you get for your slope value?
For friction or static?
The static.
0.317.
Alright, so you got 0.31. Who was at the second table? What'd you guys get for your static friction?
0.34.
0.34, and who was in the back tables?
That was our We got point.
I don't remember what it was either.
Point three, it was a 0.31, right? Or no? I took a picture of it. I didn't write it down.
So, one of the things that I noticed when I was walking around is that not only did you guys get different slopes for your 2 lines, if you compare each static from table 1 to table 2 to table 3, you guys had different slopes. Now, we all ostensibly did the same kind of lab where we pulled the thing, but why do you think the slopes were different? Check your neighbor, okay, all right, and see if your neighbor knows, okay?
Yeah.
Why do you think the slopes were different?
We used like 10. It was different. It was like 6 newtons, 11, 16, 21. So like, that's and there. What was their slope?
It's not error though, these are actually very different. And the reason we know they're different is like, it's between 10 and 20% difference between. Alright,
Sophia, it is 0.31.
Okay, that makes sense, because ours is close to theirs, and they use the same
it's
numbers.
different between those two, and the difference depends on the surfaces. Alright, why do we think the slopes from group to group to group may have been different?
Different normal.
Well, the different normal forces, those would have led to different frictional forces, right? But everybody's linear. Why do you think the slopes themselves would have been different? Yeah,
Is it because it was a different surface?
different surface combination?
Like, yeah, things you pulled it out.
What did you guys do in this over here? This first group?
Oh, us?
Yeah,
Whiteboard and felt.
felt on the whiteboard. What about the middle group?
It was wood on whiteboard?
Yeah. That sounds good.
Maybe in the back of the whiteboard. What do you guys think about George's assertion that different textures might give rise to different slopes? I mean, think about, do you think there might be 2 surfaces that would be really slippery against one another?
Yeah.
Okay? Like, what about like steel on ice?
I don't know, it's ice skating. Oh, is that how ice skating works?
Do you think steel on ice, do you think you want that to slip against one another?
Yes. It worked.
What about rubber on concrete?
No. Tires.
Right? Do you think you want that to be a lot of friction or a little friction?
Wait, a lot. Lots. See.
So,
No, a lot.
what I'm saying here is that let's consider this.
Nope. Well, you're not gonna have
Yeah, right.
And I have to do like ACT tests. Ooh, y'all.
Oh, you're right.
All right, so
I have to, I paid for it.
reset, please.
Study for it, so yeah.
Let's check out these two lines that I drew here. Okay, let's check out these two lines that I drew here. What do you notice about the purple line, ice and steel?
Very little friction.
So for any given normal force, it has only a little bit of friction. But what about the rubber on the road?
Lots of friction.
Lots of friction.
Boy.
And this one has a very low steepness. This one has a high steepness.
Yeah.
Does that make sense? Does the steepness of the line, does that determine the slope of the line?
Yes.
Yes, it does. That's what slope is. It's a measurement of the steepness. So here's where we are. The slope, okay, the slope here is what we call the coefficient of friction, and it is experimentally determined by two different surfaces. So if you did the wood and the table, you would have gotten a different slope value than if you did the felt and the table. Does that make sense? So your slope is determined by